Let's move on to our last talk of this first session by Aaron Young, whose talk title is Semi-Analytic Forecast, Uncovering Galaxy Formation with JWST and Beyond. So Aaron, when you're ready, go ahead and share your screen and you can unmute yourself.
Thank you, Steve. Sorry. Hi, everyone. My name is Aaron Young. I'm a graduate student. Oh, no. I have recently graduated from Rutgers, and I will remain in the Flatiron Institute until the end of the summer. Then I'll move to NASA Goddard as an MPP fellow this fall. So I would like to thank the organizers, especially the Steves, for making this fun escape from quarantine possible, as I'm still currently based in New York and have been locked up for many months now. In the next 10 minutes, I will give you an overview for the Semi-Analytic Forecast for JWST work series. And at the end, I'll give you a brief forecast for the future of the Forcast project. Great. So I don't think I need to convince this audience why we want to explore the very high redshift universe. There are just so many things that we don't know yet, and we are about to find out more with our shiny new tools. And JWST is one of them. So before I get to the forecast for JWST, let me first briefly walk you through the model that we used to make the forecast. In this project, we used the Santa Cruz Semi-Analytic model, or SAM, to model galaxy formation at high redshift. The physical processes that are involved in galaxy formation are tracked with a collection of physical or empirical recipes. And this includes the very standard things like the cooling of gas, star formation, supernova feedback, and many other things. And of course, we also have a new gas partitioning recipe that partitions cold gas into different phases, for example, the ionized, neutral, and molecular phase. And we also get, and we also use the molecular hydrogen as a tracer for star formation. And because the SAM is very efficient, and we also get a predictions for a wide variety of physical properties out. For example, the star formation rate, stellar mass, size, metallicity, and UV luminosity. And the list goes on and on. And since galaxy properties are being tracked in bulk, we don't keep tabs on hundreds or thousands of mass particles or grid cells. And our model is much more efficient than conventional numerical methods. And because of that, we can easily simulate millions of galaxies across an extremely wide mass range and also a wide range of redshift, and only requires a rather scalable amount of time and computational resources. So all sounds great, right? Except this is, well, this is great, but at some cost. So this modeling approach, we are not able to spatially resolve our galaxy. So we can't see the internal structure. We can tell how stars and gas are distributed within the galaxy. And SAM is not great at accounting for effects from the environment. So for now, the current SAM doesn't know about a galaxy nearby if there is one. And just track whatever physics happens within a halo or within its own merger history of the halo. Great. So we have heard a few talks about galaxies, but let me also try to take this opportunity to make a little connection to cosmic reionization. So we take the predicted galaxy population and specifically the stellar mass, star formation rate, stellar age, and metallicity. And then we use a synthetic stellar population model of our choice. In this case, our traditional model is BPAS. And then we calculate or predict the production rates of Lyman continuum photons. So this gives us the cosmic ionizing photon budget, or we can call it the source term, and in the following differential equation. And of course, there is also a sink term that represents the recombination of ionizing hydrogen, ionized hydrogen. And solving this equation gives us the bulk estimate of the cosmic reionization history as a function of time. Great. So this model is certainly not new. It's been developed quite a while ago, but here there are a few things that we did slightly differently in attempt to make this model a little more physical. So first, our galaxies are sourced from a physically motivated SAM. So we sampled objects across a very wide mass range, and this means we're doing few extrapolations, but rather to make sure our galaxies are physically backed. And secondly, the production of ionizing photons is calculated based off the star formation history of individual galaxies. So we can capture more of the correlation and scatter of Lyman continuum production rate and other galaxy properties. And overall, there are fewer smoothings and fittings. So we simply sum the contribution of all our predicted galaxies instead of having to integrate over the fitted UV luminosity functions. So that all helps a little bit. All right, so here comes the result. First, let me show you our predicted UV luminosity function at redshift 4 to 10. The blue solid lines are the predictions from our fiducial model. The dashed lines show what happens without dust. And of course, the data points are from observations. We see that 3 parameters in our model are only calibrated to redshift 0, but these predictions are doing, I would say, reasonably well, but it's actually exceptionally well matching observational constraints, and this is non-trivial. And these predictions extend to very faint magnitudes that we hope in the future JWST will be able to finally reveal. All right. And because the SAM is super efficient, we can also explore how results are impacted by different model assumptions and by doing some controlled experiments. So we know that stellar feedback is a main mechanism that can suppress or boost the number of faint galaxies. And the equation in the box here is what we use to track mass outflow due to supernova feedback. And in our experiment, we changed this one particular parameter, alpha reheat, to explore alternative scenarios where the strength of the supernova feedback is stronger or weaker. And we then provide a range of predictions that are still permitted by the current sets of observations. And hopefully in the future, JWST will be able to narrow that down by a lot. Great. And last for this part, I just want to quickly flash a collection of cross correlations that we predicted for the many physical properties we get out of the SAM. The cyan and purple lines mark where we expect a JWST wide of view deep survey will show us. And if you're an observer, you might find the bottom row handy, as it shows a range of some key corresponding physical properties for galaxies at a given observed magnitude. Okay, so those were the galaxies, and let's switch gear a little bit to talk about reionization. So the theme here is to try to understand and perhaps to disentangle the 3 moving parts that have significant impacts on the overall cosmic reionization ionizing photon budget a little bit. Let's start with the figure on the left. There's one figure right now. The first moving part is the production rate of ionizing photons, which has to do with the physical properties of the stellar populations and how it's translated to the number of ionizing photons being produced, and which depends largely on the assumptions that went into the synthetic stellar population models. So here I show you 2 examples. The blue line is our fiducial model with BPAS binary, and which accounts for binary stars, obviously. And in comparison, we also show you an older model that the purple line is the model that only accounts for rest UV magnitude. So it's just taking the magnitude of a galaxy and translate that into the number of ionizing photons being produced. Okay, so we already see that there's a little difference, but we don't stop there. So the second moving part is the number of galaxies that are out there. So from the last slide, we know there are, well, they're quite literally, we're asking how many galaxies are there in the high redshift universe. And we saw that the supernova feedback mechanism can have a huge impact on the fate and slope of the luminosity function. So this is basically the same from what we saw from the last slide. We ask what will the ionizing photon budget be with these different predicted, the range of the ionizing, of the UV luminosity functions. And of course, the last part, we allow the alignment continuum escape fraction to vary from 5% to 80%. So note that for this part, we just let the escape fraction to be a constant over time and for all galaxies. And this already shows us this. For the entire set of this controlled experiment, we only vary one thing at a time, and you can very clearly see how each part, what role do they play in affecting the global ionizing photon budget. All right, so on the right, we then jam this whole thing into an MCMC hammer, trying to figure out the optimal configurations that are needed to reproduce the set of current observations. And the top panel on the right shows you that all we need is a redshift dependent escape fraction that evolves from a few percent to a 25% at high redshift. And of course, what is nice is the predicted alpha reheat is quite similar or very close to our fiducial value. And this is what it all takes to reproduce the current set of observations for observed constraints on reionization history, which is great. I'm happy. All right, ultimately, we want to answer some of the questions. For example, like what fraction of ionizing photons are coming from the detected galaxies? So for example, here we can see for a JWST deep survey, we are expecting, well, on the left, we're expecting maybe about 40% with galaxies that are expected to be picked up by JWST in a deep survey will be accountable for about 40% of the overall ionizing photon budget at redshift 10. And this goes up to about 80% at redshift 6 toward the end of reionization, which is great. So we are looking at galaxies that are doing most of the heavy lifting. So similarly on the right, I break down the predicted galaxy populations to 4 groups and their rest UV magnitude and to plot their contribution as a function of redshift. And we can see that galaxies that are contributing the most ionizing photons are not the brightest ones, since there are only very few of them. But it is slightly fainter. It is the slightly fainter ones that are doing the heavy lifting, which are both very prevalent at high redshift, and also they are quite efficient at producing ionizing photons. Great, so there are so many things I want to cover, but I really have to let some of those go. But I do encourage you to check out the work series. They're all been published or accepted. And before I go, I just want to use 2 more slides to show you some exciting future work that we plan to do. So there are 2 parts of the plan. One is to keep working on the Forcast project to make SAM a platform for multi-instrument exploration. So I'm happy that the newly renamed Roman Space Telescope will proceed. And we now have these 2 square degree light cones, which is a simulated field with the good south field in comparison on the top. And you're looking at galaxies with positions in the sky and also a redshift gradient. So we can now use these new light cones to explore some large survey exclusive science, such as clustering. But also there's a separate theory project called Samurai, which is what I'm going to do at Goddard, which stands for SAM with ultra high redshift astrophysical interplay. We'll be implementing a few hopefully more high redshift exclusive or very important physical processes at high redshift. So to make the model more physically representative for the high redshift galaxy population. All right, so I will leave you with the conclusion and outlook. I know I'm running out of time, but please do reach out to me. I have a new email address, and looking forward to answer any questions.
All right, thank you, Aaron. So a couple questions on the escape fraction. So from Maxime Tribich, have you tried to implement an escape fraction dependent on galaxy properties, such as stellar mass, specific star formation rate? And Christian Finlater says, along those lines, is a redshift dependence still required, even if a mass dependence is allowed?
Thanks for all those questions. I've gotten those from co-authors, from the referee, from the editor, and also from everyone who's have seen this work in the past. Yes, that was the plan, but it turns out to be too messy, and I probably won't be able to finish that when I graduate. But we do have a few plans that goes from very simple things to have the escape fraction scale with individual halo mass, or even with dust. So there are so many venues that there are so many directions that we can take this. And I'm really excited about building a slightly more sophisticated and more physically representative escape fraction model, but we want to do it right. But yes, if you want to talk more offline and give me a little input how to do it, I will be super happy.
Great. All right, well, thank you, Aaron. And that concludes this morning's session.